All right. Everything coming through. So
Yeah.
I think what is good news for most of you today, and bad news for those of you out there that love to talk about the details of numerical optimization. Um, Today's presentation and tutorial is going to be focused more on the use cases and practical application of PyCalphad. Of course, love to discuss at length a lot of the details of the numerical methods and everything, and have published on this. And I'm happy to refer you to publications if you'd like to learn more. But today, it's really going to be about the hands-on use cases and how you might be able to make PyCalphad work for you in your own research. And so the place I'd like to start is, to say, what is PyCalphad? So PyCalphad is a Python-based tool for CALPHAD modeling, including multi-component. The thing that I think makes PyCalphad unique, the reason why it was created, was in order to make the internals of the system, including the models of the Gibbs energy, actually accessible to the user and be able to be modified. And we'll see a little bit about what I mean by that later during the tutorial. It's been in continuous development since 2014. As Dr. Liu mentioned, it started as a project when I was a graduate student. I was fortunate when I graduated and joined NASA JPL in 2016. I've been able to continue to find funding to support the development activity. And not only that, even receive recognition for the team for PyCalphad within JPL in 2019. It was JPL's Software of the Year. It went on to represent JPL in a NASA-wide competition where it received runner-up. And that was pretty gratifying and exciting that PyCalphad's now on a list that's previously had things on it like the flight control software for the Mars rovers and really space grade space mission type stuff. And then PyCalphad is now on that list as measured by the impact that it's been able to make on the community. PyCalphad is a free and open source software. It's developed in the open. It can be found on GitHub. It wouldn't be where it is today without the support of the members of the PyCalphad development team, which include Brandon and also Dr. Liu. And we have a website, pycalphad.org, where you can find a lot more information about the software, examples, how to download and install it, and other relevant information. So kind of the reasons to use PyCalphad in particular over, say another software package is PyCalphad really enables you to do new types of research. You're able to access information inside the models that other tools just don't offer you that level of granularity. You're able to actually programmatically access not just the results of calculations, but the energy models, information within the databases, and there's this kind of access enables you, not just to perform CALPHAD calculations programmatically, but interact with CALPHAD data programmatically. In what I think, in my biased opinion, is the easiest way available. The other thing is because it's free and open source, the code can be deployed anywhere without restriction, including in high performance computing environments, computing clusters, and things like that. Some interesting use cases. So these are just a couple of the use cases that I've come across that have been published. There's a group that's built a face field tool that they've been using for research on top of PyCalphad. This is a group at Rensselaer Polytechnic Institute. Their software is out there on GitHub, and they're using it to make advances in face field modeling. There's been a group that's been exploring new ways of using CALPHAD free energy information to predict coherent solid-solid and solid-liquid interfacial energies. And then also there's been work in building kind of these multi-phase property models using CALPHAD data. So in this case, two-phase elastic constant models for nickel-based superalloys. And so a lot of kind of interesting and exciting use cases. And the thing that's really gratifying to me about these use cases is actually there's been pretty limited interaction from the development team. So these are really community use cases, people being able to take the software and use it on their own to make an impact and create new research. So here's another example. This is some work I've been involved in recently, along with Brandon and Dr. Liu. So this is an example of doing work looking at CALPHAD assessment process. This is chromium nickel binary system, and in this case, we're just talking about using SBAY, and you'll hear more about SBAY, but it's a tool for CALPHAD assessment. You'll hear about it in a later sequence if you haven't already heard about it previously, and I imagine many members of the audience here have. And so the idea is we're starting here with this initial guess for what the model is. We have all of this phase equilibria data, and then we're able to refine the solution and get something that's a better fit to the experimental data. And so this is something that has been relatively known, but what PyCalphad enables us to do now is we can actually explore what's happening during the assessment process at a higher level of granularity. And so, for example, we can actually compute what we're calling partial sensitivity maps, where we can actually map out the individual phase equilibria points and compute sensitivities for them relative to the different parameters in the assessment process. This is some work that we hope to have published pretty soon. We're just waiting to hear back. But this type of calculation, this sort of work, is only possible because of PyCalphad. And now let me show you guys a non-interactive example here. So what we're looking at now is a computational notebook. So what we're looking at is non-interactive at the moment. But this analysis essentially constitutes the supplementary material for this publication on sensitivity estimation that we expect to have published very soon. And so I'm not going to walk you through everything, but what we were able to do because of PyCalphad and also SBAY was generate a completely reproducible analysis for all of the key figures and tables in our book. And so the code here, and there's some supporting files here that are also able to be downloaded. The code here enables you to completely reproduce all of the figures and the analysis that are in the publication. And so this really tells you right away, it provides you all the information. Besides showing you how the calculation was done, it gives others an opportunity to audit and confirm the integrity of the work, to compare what we did to the equations in our publication. And also, you know, they could actually take this work and build on it in order to do something else, which is something we plan to do ourselves and ultimately incorporate more sensitivity information into our tools. But in terms of what the research community is able to do, I think that this is an exciting development for reproducibility within the CALPHAD community. And our hope is to be able to get the community excited about this way of communicating results, such that we can dramatically improve the reproducibility and reusability of CALPHAD modeling work. And so this is kind of one of the additional benefits that PyCalphad enables, is the fact that it can be used in this sort of a computational environment. And so this is a a non-interactive notebook. So in this case, you would need to download it and load it up in a PyCalphad environment in order to do anything. And of course, there's information on the PyCalphad website about how to do this. But if we would like to be able to do something interactively, we now have available in a limited beta. In fact, this is the first time we're really talking about it with a larger group, is our Try PyCalphad website, which is powered by Binder, which some of you may have heard of, which is a cloud-based computational platform. And what this is doing now is firing up, and you can please feel free to follow along, by the way. It fires up a custom one-time computational environment just for you that you can interact with. And as soon as you close the window, the environment goes away. So it's kind of a throwaway, test out, demo type of computational environment. And so in this case, when we load it up, it's preloaded with a bunch of examples, and all of these examples can be run and used. But what I'm going to do right now actually is close all of these windows just so that we can start for something a little bit simpler. And so if you have any familiarity with Python, you know about importing. And so what I'm going to do to start is to just import a couple of objects that I need in order to start interacting with the CALPHAD. And so the first thing, as you know, in any type of CALPHAD modeling process, is we need to load a database. So what I'm going to do now is I'm going to load this aluminum copper yttrium database. And then I'm going to hit Shift plus Enter to run the cell. And now my database is loaded. And so what does it mean that my database is loaded now? Well, now I can interact with this database object. I hit Tab and I can see that this object has a bunch of attributes. One of the attributes it has is the phases that are in the database. So I can see this is the list of all the phases that are in the database. I can also see, well, these are the elements, the pure elements that are defined in the database. I'm also able to go into a more detailed level of granularity. I can pick a particular database, and then I can look at the constituents. I can see that this aluminum copper theta phase is 2 sublattice phase, and that these are the species that are defined. And I can even interact with it programmatically. Look, that's the first sublattice, that's the second sublattice. Moving on from there, once we have a database defined, we might like to be able to then create instances of Gibbs energy models. And so for that, we use the model object. Now, I may not know how to write all the arguments to define the model. So I can hit inside this Jupyter environment, Shift plus Tab, and it brings up an interactive documentation window that tells me the order of the arguments and what each of the arguments means. I can also go on the pycalphad.org website and look up the information and copy paste from examples on how to do this as well. And so what I'll do is I'll write the database, and then I'll say I want aluminum and copper, and I want to create an instance of the aluminum copper theta phase. And I run that, and now the model is loaded. So what sort of things am I able to do with a model object? Well, one of the things I can do is I can get the expression for the Gibbs energy of the whole function, which I will get it in this mathematical notation, and I will see, oh, it's actually kind of big. There's lots of temperature breakpoints. So I may not, this is not necessarily something I would want to pull up just to look at it all the time, but it shows me that this is available to me, and it's available to me in symbolic form. I can also interact with the object. I can say, I just care about what's happening at 1200 Kelvin, and it will substitute the temperature variable in and multiply through the temperature and give me this more specific result. I also have the ability to compute derivatives. using some symbolic math. So I can compute a temperature derivative. I also have the ability to compute derivatives with respect to the site fractions. And so I can actually get all of these derivatives symbolically. In fact, under the hood, this is what PyCalphad is doing when it's computing equilibrium, is it actually is calling these same functions in order to generate all of the derivatives and second derivatives at runtime. And so you're able to leverage this common calculation framework to actually be able to control how the calculations are performed. Not only that, we can go further. If we wanted to look at, and this is more relevant as you start thinking about the assessment process, is I may actually want to look at what would happen if I wiped all the symbols from the database and I wanted to look at the Gibbs energy expressions then. So if I reset and run through there, and now all the symbols are cleared. And what I notice now when I compute the Gibbs energy is I can see these GALBCC term, and then also my SCR reference state terms are also here. In this case, that's what's defined in the database. And then the rest of what I see here, those are the interaction parameters that were not defined inside of a function. So they're still shown here. I can treat now these undefined symbols like any other symbol and differentiate with respect to them. So for example, I could write what's the derivative of the Gibbs energy with respect to this term, and it will give it to me in symbolic form also. We have other properties defined for the models as well, and there's a full list on the website. Another thing we're able to do is, we can do entropy and enthalpy and so on. And you're also able to have PyCalphad generate these results numerically and have plots. But this is the foundation of what PyCalphad is able to do, and part of what makes it so powerful for CALPHAD modeling. To move on to another example, I'll show you about PyCalphad's reference state support. And now what we're looking at is a computational notebook, and we can see that inside of the notebook, I'm mixing code and computation together. So I can see that this text is, I can edit it just like I can edit code, but here it provides me important context for the calculations. And so now we're getting into a little bit of a more detailed, more involved calculation here. But what I'll do is I'll walk everyone through it. This first line is just telling the matplotlib backend to put all the plots in line, which is necessary for this online example. And so what we have here is we have a database. And so in this case, this is a niobium rhenium assessment from Xuan Liu a couple years back. We have the ability to define reference states within PyCalphad the same way that you would in any other software. And so in this case, these reference states are being defined relative to the liquid phase in this database. And now what we're able to do once we've defined this reference state is we can take our familiar model object and we can call the shift reference state function on our model object, which will now manipulate the energy functions such that when we do our calculation, we now have the desired reference state. And so just like if you were to use thermocalc, for example, by shifting our reference state, we can now call out the output functions with this R suffix. So HMR here meaning the molar enthalpy at a defined reference state. And so in this case, it's defined relative to the liquid, so that when we finally go through and compute the liquid mixing enthalpy, we see here that the reference state has indeed been shifted to that of the liquid pure elements. So just to walk through a little bit of what's going on here. When we define conditions, what we're doing is the same way that you would set conditions in another software is we define a pressure, which is in Pascal. We define temperature, which is in Kelvin. And then we can define mole fractions. And so in this case, we're defining it in terms of mole fraction of rhenium. And then we write our start rhenium content, our end rhenium content, and then the size of the step. And so that is what the conditions here mean. So next what we do is we call our calculate function. And what our calculate function does is it is actually performing the property computation. And then down here, if you've seen Matplotlib before, this probably doesn't look too different for you, except for these calls down here are basically defining the X and the Y information. And so if we run this, we can get a sense of about how long this calculation takes to run. It's pretty quick. And now we get our niobium rhenium liquid mixing enthalpy. More advanced calculations are also possible. Just to show you, I won't. Yeah, I have time. I'll go through this also as well. And so this is another calculation where now we're defining the reference states here, niobium, the BCC, and rhenium, the HCP phase at this particular temperature and pressure. And then what we're doing is we're creating custom models for all phases and then shifting them by the specified reference state. And so this is how to do calculations with reference states inside of PyCalphad. And after we've shifted these reference states, we save them inside this dictionary, and then we pass that dictionary to the equilibrium function. So we haven't talked too much about the equilibrium function at this point, but it's basically the computational heart of PyCalphad. It's the thing that solves the Gibbs energy minimization problem. The goal is to try to have the user not have to specify options unless they're doing something different. So by default, the equilibrium function thinks that you just want to compute the phase fractions and the Gibbs energy. And if you want to do something different, then you tell it. So in this case, we're doing something different. We're computing the enthalpy, not just the Gibbs energy. And then we're also passing in our custom model objects with modified reference states. And then down here, we have some plot wrangling that's going on in order to get ourselves this nice color-coded convex hull plot where we have the formation enthalpy as a function of rhenium content at fixed temperature. And so PyCalphad gives you a lot of power in terms of the ability to pull the results out of the calculation and also to then plot them. And then we have some other, let me move on. To give you a little bit of a sense also about the results of calculations, I'll go through this really quick. Again, all this information, besides the fact that you can load it up here on this try PyCalphad interface, is also available on the PyCalphad.org website. But this is our interactive documentation for the results of calculations. So when you call the calculate function or when you call the equilibrium function, what you get back are actually multidimensional array objects that are labeled. And so what this lets you do is it's almost like having an interactive spreadsheet of data where you have multidimensional columns. So you have the ability to slice and dice, index these objects in what we think is the most powerful way available right now for working with CALPHAD data. And so we have a lot of information here, but you got to get a sense of when you call the equilibrium function, what is the result? And so you can see this, this truncated representation of the object here. We have all this information. we have, the phase that's at equilibrium. We have the amount of the phase. And so here the symbols are similar to what you might see in another CALPHAD software tool, chemical potentials, and then also the enthalpy, because we specifically requested the enthalpy. You can do things like do calls and use this where function and say, give me all of the phase fractions where the phase is equal to FCC, almost like you're writing a database query. You can basically get this information, and then you get back these array objects, and you can later go on and save them or plot them or do any sort of work that you'd like to be able to do for analyzing the results. Moving on also to cementite, the cementite example. We also have the ability, you don't just have to have the TDB files in a separate file. You can also embed them as multi-line strings here. And then when you call the database function, you can just pass in the multi-line string. This is sometimes convenient, especially if you're working with small databases and you just want to make a small change and then go back. You have everything nice and self-contained in one file, like it is for this example. And so in this case, we're plotting heat capacity for the cementite phase. And so we can see here the temperature. It's being plotted from 1 Kelvin to 2000 Kelvin and increments of half a Kelvin. And this is also just showing off the fact that you don't necessarily have to write an abbreviated symbol. We also have support for these kind of extended text descriptions that's a little bit easier, a little bit more human readable as well. And so now we can go on and then plot the heat capacity. And so we can see the figure here. And so this is more or less how, and the plotting and the theming and everything for this is all able to be updated. We also have support for multi-component databases and more sophisticated calculation types. So in addition, we have the capability to perform Scheil solidifications with an accompanying package called Scheil. So this was some work that Brandon really spearheaded not too long ago. And so in this case, we're looking at the aluminum zinc system is convenient to work with, and so we can plot the phase diagram. We're able to perform equilibrium solidification calculations and look at the solidification path, but then also to perform Scheil solidification and compute these Scheil solidification paths as well. And so you can see here, these are estimated wall times. So if we ran this in real time, this is roughly about the amount of time we would expect it to take you to run. And then you can also get the results and phase fractions here also. So there's a lot that we're able to do and build on top of PyCalphad here. I mean, of course, how can I forget for CalPhad? We of course also have the ability to compute the phase diagrams with a built-in function called binplot for binary systems, and also for ternary databases, or ternary isotherms as well. Although this is still kind of slow, we're working to make this step a bit faster as well, and we hope to have a new release out before the year is over, with some of our new performance improvements and feature improvements as well. So to kind of give you, in addition to my call to action for you to try PyCalphad and figure out if it's something that is relevant to what you do, I also want you to know an extended invitation to come and talk to me and Brandon and the PyCalphad community. We have a chat channel on Gitter, which is gitter.im, and then /PyCalphad, and then it will bring you to this channel. You can sign up either on GitHub And then I think also they have support for some other user accounts as well that you may already have, but you can log in and start posting and asking questions on here, and very often get responses quickly to your questions. And also because it's public, you have the ability also to help others with your question. Of course, if you'd rather ask your question in private, you're welcome to email me as well. I'll make sure that this group gets my contact information after this as well, in case you guys have questions. So this is about all I've prepared for the sort of formal guided part of the presentation. I know we went quickly, but I really wanted to focus on the things that you can do and the information that you can get access to, and then maybe sort of focus the discussion based on people's questions, and maybe even show some examples in real time, depending on people's interest. So thank you for your attention.
All right, thanks a lot, Richard. Thanks a lot. As I hope you can see that it's very, very interactive. You can do so many things there directly by writing a line there, and you could put text there too. Maybe we first see if anybody else has a question to start.
Yeah, Dr. Lu, this is Sadash Shankar here.
Hi, Sadash.
Thank you for inviting. I really appreciate it. It was informative because I'm getting into the community a little bit through these discussions. So I had a few questions, if I may ask, on the presentation for Richard.
Yeah, go ahead.
Okay, so you showed a ternary phase diagram. So maybe let me ask the higher level questions. The thermocal connection to PyCal, is that a easier connection, or is it something that are two separate ways that you run the information and then kind of link it, or how does it work now?
Sure. So the way I understand your question is you were asking about the connection between PyCalphad and thermocalc. Is that correct?
Correct.
Right. So PyCalphad uses a completely separate custom thermodynamic engine. The TDB reading and writing, Gibbs energy, minimization, plotting, everything is completely independent of thermocalc. You do not need a license of thermocalc to run PyCalphad.
Okay. Then the other thing is if some, I mean, this is something, of course, I need to talk to Dr. Lu as well. If you were to develop some other module, how easy and how modular is it for me to essentially have run this or pass information back? I mean, how modular is it? Because, you know, I led a large research effort at Intel before. So we had the ability to integrate almost anything under the sun in terms of what we could do from university collaborators with what my team was developing. So I'm wondering how this is set up.
Sure. So, you know, I would say that the level of difficulty depends a bit on exactly what the nature of the module you want to create does. So, like, for example, one of the examples we have on the website is creating CALPHAD-based models for viscosity of liquids.
Okay.
And so I don't know if creating a new property model or adding physics is the type of integration you have in mind when you talked about a new module.
Yeah. So I have actually several things in mind.
Okay.
Maybe I could illustrate that so that it becomes a little tangible. One of the things is probably you mentioned about elastic properties, I think. So there may be an elastic property that we may want to extract as one. The second thing is quite a bit of my work is increasingly going towards the chemistry side of things. So we may use certain other constants or models that we would like to look at chemistry, but on the other hand, we would like to look at the thermodynamics aspect as well.
Mm-hmm.
And then these are just examples, which I think, based on what I heard you say, I did not think there were any problems. They are probably straightforward. Would you say it's fair?
So I think that that's a fair characterization. And so what I'll do is I'll try to give you some more reasons why I think that PyCalphad is a good tool to have in the mix for that. So in this viscosity example here, we try to be a fair tutorial. We also include common errors that a user could make, and then we show you how to fix the errors. But I'm going to skip that
that's
part.
nice. That's
I'll
nice.
skip the part right now, just to get to the gist of it. And so we have some examples here. So we talked about this model object, but the thing is, the model object can actually be subclassed. And so you have the ability to hook into PyCalphad's model building infrastructure and directly interact with the TDB file, the thermodynamic database, to pull out parameters. If you want to drive your model from a TDB file, you can do that. You can compute all of the quantities you need symbolically using the same capability I illustrated earlier. So in this case here, I actually am defining this excess entropy term because that's what I need for the model. And then down here, I just write that the result is equal to this eta times 1 minus ks excess entropy. And then look up here. I mean, it's exactly this term right here. So I basically just wrote this in symbolic form and pass it to PyCalphad, and PyCalphad handles everything else for you. It'll compute the derivatives if it needs to in order to solve the minimization problem. It'll do variable substitutions. Anything that you could do that PyCalphad can do with the built-in models, you can also do.
Very nice.
And this is not possible, I think, even now with like the latest commercial Python-based APIs, you don't have this level of access into the calculations.
Yeah, but also there is some excitement in working with Dr. Lu's group and you guys, right?
Sure.
So there is a research component which, you know, I'm still half academic, so I would like to have the research come out of it as well. The one specific thing which you don't have, at least I didn't see it, so is something like there are a lot of this thermodynamic phase space is very rich, even for something like a ternary system, that if I were to map, I mean, I'm trying to find the right way of saying this without invoking a lot of jargon. If I were to go from one ternary system to another ternary system, can I set up, by the way, we have done things like this back at Intel. So I'm just asking, how easy is it for me to do it without putting too much time into continuing? Let us say I want to go from ABC to ABD as a ternary system.
Sure. So let me respond to that with, so first, the support for multi-component systems is there. And so to perform a calculation involving going from an ABC to ABD system, I would need a database that contains ABCD. So
you would need an ABCD. Okay.
Yes. So but if that database does not exist, we do have tools available that can help you to build those databases. And so that's what the SBay tool that is also,
sorry, I didn't hear it. What tool is that? SBay?
SBay, yeah.
Yeah, we're going to have it next week. Next week, we're going to have a seminar on the SBay.
Okay.
Yeah.
Okay.
Yeah.
Thank you, Richard, for.
Yeah.
And actually, Sadas, you touched the fundamental I think it's a very fundamental a topic why we develop PyCalphad. It's one of the fundamental problem we want to do is to develop a multiple database and
That's right.
revise it. That's important.
That's
The second one is the model. And the model now in the current, all the software, the model, they are hard-coded in the software.
Mhm.
So if you want to change anything about the model, you cannot do it. You have to wait
Right,
until
right.
the
You're
vendor
right.
put it in it.
You're right.
As Richard mentioned here, is that is the symbolic computing is outside. So you can write your code, write your software here. You don't need to change anything about software.
No, I completely saw it as he was explaining it, and thank you for elaborating that.
That's really very important.
I should also add, I realize I now looking at this, I can't believe I omitted it. The other thing we're able to do here, and one of the main use cases for PyCalphad in research right now is actually uncertainty quantification. So PyCalphad is enabling a lot of work in uncertainty quantification of these predictions. So we've published work, and a lot of this has been in collaboration with Argonne National Lab, Maria Stan and Noah Paulson. We've done a lot of work in doing things like putting error bars on phase diagrams based on